Welcome. This is the regression analysis course. My name is Nicoleta Serban. I'm associate professor in the Stewart School of Industrial and System Engineering. This is a multiple regression lecture, and I will illustrate multiple regression with an example related to ranking states by SAT performance. In this lesson, I'll focus on introduction of the example, as well as I'll focus on bias selection and exploratory data analysis. In 1982, average SAT scores were published with breakdown of state-by-state performance of SAT in the United States. The average state SAT scores vary considerably by state, with the mean scores falling between 790 for South Carolina to 1,088 for Iowa. Two researchers examined compositional and demographic variables to understand to what extent these characteristics were tied to SAT scores. The research questions addressed in this example are: which variables are associated with the state SAT scores? How do the states rank with respect to the SAT performance? Which states perform best for the amount of money they spend? In this example, the response variable is the state average SAT score, and the predictive variables are as follows: takers, which is the percentage of total eligible students in the state who took the exam; rank, which is the median percentile of ranking of test takers within their secondary school classes; income, which is the median income of families of test takers in hundreds of dollars; years, which is the average number of years that the test takers had in social sciences, natural sciences, and humanities; public, which is a percentage of test takers who attended public schools; expend or expenditure, which is a state expenditure on secondary school in hundreds of dollars per student. Back in 1982, not all colleges used to require SAT for admission, particularly those in Midwest. This resulted in that the states with high average SAT scores had low percentages of takers. The reason is that only the best students planning to attend college out of state took the SAT exams. As the percentage of takers increased for other states, so does the likelihood that the takers include lower qualified students. Thus, in this example, two variables can be used to control for this bias selection, which are the percentage of students taking SAT or takers and the median percentile of ranking of test takers within the secondary school classes, which is rank. We'll first read the data in R using a read.table command in R, where we need to input the file name, and we need to specify that the file name, the columns in the file name, have a header. In order to check the data, I read out the first 4 rows of the data, and you can see the columns in this in a data matrix. We can check the dimensionality of the data file, which consists of 50 rows, each row corresponding to a U.S. state. We will attach the data here in order for R to automatically recognize the columns in the data as individual vectors. Exploratory data analysis allows us to look at the variables contained in the data set before beginning any formal analysis. So for exploratory data analysis in this example, we'll first examine the variables individual through histograms. For each variable in the data, we plot its histogram. With the histogram, we can see the general range of the data, shape, such as skewedness, as well as any other potential trends. So those are the histograms for the SAT scores in black and for all the other 6 predictors. From these histograms, we note that the state average SAT score has a bimodal distribution, and this is potentially indicating the clustering of states depending on whether colleges in the state require SAT or not, thus potentially due to the bias selection. Following on this line of thought, we can see the takers, the next histogram, that this variable has clearly 2 clusters, which may explain the modality in the SAT score average as well. We can note also that one state has almost double the amount of secondary schooling expenditure compared to all the other states. And this is actually Alaska. Similarly, we can single out one state that has very few students coming from public schools taking the SAT score. The state is Louisiana. We can also look at all the variables together. We can do this by using a pairwise correlation, by using the command in R. But we can do a scatter plot matrix of all the variables, including the response and the predictive variables. The scatter plot command that I showed you in the previous slide outputs a scatter plot matrix showing the relationship between the variables. Generally, we're looking for trends here. Does the value of one variable tend to affect the value of another? If so, is that relationship linear? This type of questions help us think of what type of interaction and higher order terms we may want to include in the regression model. We can also evaluate whether the linearity assumption holds and whether there is strong collinearity among the predictive variables. The scatter plot matrix that we see on this slide shows clear relationship between SAT, the response variable, and takers and rank, which are the two variables, the two controlling variables. Interestingly, we can see also that Alaska shows up as a high value in expenditure. And we can see that Alaska has a rather average SAT score despite its very high levels of spending. We'll leave Alaska in the model, in the data set but a more complete analysis would seek to remove outliers and high influential points. In fact, this data contains two rather obvious outliers, one feature visible in both the scatter plot and the histogram in the gap in the distribution of takers. When there is such a distinct gap in a variable's distribution, sometimes it's a good idea to consider a transformation from a continuous variable to an indicator variable. Since subtle trends are often difficult to identify in the scatter plot matrices, sometimes a correlation matrix can be useful. From the correlation matrix for this data, we note that both the income and the years variables have moderately strong positive correlations with the response variable SAT. The respective correlations are 0.58 and 0.33, indicating that higher levels of income and years of education in sciences and humanities are generally associated with higher trends with the SAT scores. However, this does not imply causation, and each of these trends may be nullified or even reversed when accounting for the other variables in the model. A variable such as years may be of particular interest to researchers. Although neither science nor humanities are directly tested on the SAT, researchers may be interested in whether an increase in the number of years of such classes is associated with a significant increase in an SAT score. I'll come back to this point in a different lesson. In summary, in this lesson, I illustrated multiple linear regression with an example with a focus on correcting bias selection using controlling factors and performing exploratory data analysis. Thank you.